So here we are. I would like to start with a brief introduction of Dr. Sriram. So Dr. Sriram actually was here in a very short notice, and we are glad you could make it. Thank you so much for being here. Dr. Sriram holds a PhD degree from Cyprus University, New York, and he is currently a senior research engineer in the Advanced Networking Technologies Division at NIST. He's worked on quite varied technologies and in depth in various domains. Some of his main focus has been on the border gateway protocol, architectures and protocols in also traffic management, algorithms, simulation, and performance evaluations for internet and wireless technologies. Design and evaluation of internet routing architecture, protocols, and security has also been a major focus of his work. So we are really glad to have you here. Thank you so much for your presence. And we would, without any further delay, we would like to start.
Thank you. I can stand in anywhere here.
Yes.
Yeah, you can stand.
Oh, you need to watch this. Okay. So good evening. I'm very happy to be here this evening with all of you. Um, so this is work that I have been involved with both at NIST and also in the IETF for standardization. So I will speak about the routing security vulnerabilities, and then also the solutions that are being worked both at NIST in our group as well as in the IETF, where we are substantially involved with standardization. So this is my team. We have been working on several aspects of BGP robustness and security. So I'll walk you through some of that today. Yeah, okay, still to go an hour to 7:30. Page down. Not good. Okay, so first, in general about internet security or cyber security. So the internet security issues can arise at different levels, such as end users, consumers of information. There could be problems with password theft and things like that, and as well as phishing attacks on end users. Then at the application level, again, email phishing attacks are possible. Web browsers may be compromised, and also attacks related to voice, video, etc. As well as at the at the enterprise information systems level, campus networks, cloud services, data centers could be compromised, where you need enterprise cybersecurity detection as well as mitigation. So finally, the internet backbone, where you have enterprise networks, carrier networks, they are interconnected with, each has its own autonomous system, and they are interconnected with the border gateway protocols. The border routers speak the BGP protocol in order to exchange reachability information. So they have vulnerabilities as well as domain name systems on which the internet services heavily rely. They have vulnerabilities as well. So you perhaps know DNS has the DNSSEC as a solution. So today we'll focus on the border gateway protocol or BGP protocol, the security for that. We'll look at the vulnerabilities and then also discuss the security. Before that, let me just mention that as far as can we fix this? Yeah, just scroll it down a bit. Oh, yeah. So NIST, I just want to mention before I jump into the routing security, BGP security topic, let me just mention that for the cybersecurity for enterprises, NIST is also doing very good work, and a lot of industries, Fortune 500 companies, a large percentage are already implementing some of these recommendations from NIST. So you might, if you are interested in general about the enterprise IT infrastructure security, if you would like, I mean, I would recommend taking a look at the cybersecurity framework document. I know some of you have already looked at that. Also make use of it. And also NIST has a special publication 853 that has to do with security and privacy controls for federal information systems. Just to give you a quick glimpse about what is in the cyber security framework. So essentially, there is problem identification. This is a high level snippet from the document, just to give you a glimpse of what is there. So you need to identify what the security vulnerabilities are, and then come up with a screen technology, implemented technology methodology to protect. And then once protection is provided, then there could still be attacks, zero-day attacks, for example. So you need to have the detection capabilities as well. And then once this attack is detected, we have to have techniques to respond to the attack, to mitigate it, and then recover from the attack. So that is a whole lot of details related to each of these steps is provided in that document. So that document is not the main topic, but I wanted to mention about that because it is an important aspect of NIST work, and it's an example of how NIST standards related documents are highly useful across the industry. And so now I will also talk about other documents and standards as well. So let's jump into this topic of internet infrastructure vulnerabilities. So here we're going to focus on the BGP routers, where we have the vulnerabilities in terms of prefix hijacks and misrouting. I will explain in a moment what that is about. Then there is a distributed denial of service attacks by flooding servers with IP packets and often with spoofed addresses. And this is something that can also be mitigated in the routers. So that's why I'm going to talk about that. Things that you can do in the BGP router to make the internet infrastructure more secure and robust. And then you have DNSSEC, for example, but then there are other techniques that go along with the DNS for the DNS servers that make the internet servers. I mean, there are DNSSEC especially can be exploited for DDoS attacks to generate large amounts of traffic towards the target. So these are the various vulnerabilities, and we are engaged in the community as a whole is engaged in many tech solutions that are standards based. Several standards have already been published, and more standards are still being worked on in the IETF. So I'm going to walk you through some of that today. So just to, how many of you are familiar with border gateway protocol? A few. So I'll give you an introduction to, quick introduction to what BGP is, and then we'll look at the vulnerabilities, and then we'll look at the security solutions to address those vulnerabilities. So just to give a brief intro to BGP, so let's say that the network on the left is a /16 IP subnetwork, So the company owns a slash 16 IP address space. It announces, let's call that S star. It announces the S star into the internet, and AS2 is the neighboring AS of AS1. AS2 receives the update and then propagates it to its neighbors. And in order to propagate that reachability information, so essentially, like AS1 is announcing its prefix in order to have reachability for its network throughout the internet. And the BGP protocol is used for that. And AS2 also uses the BGP protocol with other ASs in the internet. And that is how the announcement of this network on the left propagates throughout the internet using the border gateway protocol. So that's, and then each of these networks also have subnets or address space that they would like to announce where their servers reside. And these addresses are announced throughout the internet as well in BGP. BGP is a distributed system, and as these messages propagate in BGP, all the autonomous systems throughout the internet, they learn about the reachability of all the address space that is allocated and announced in the internet. So that is the basic glue. So BGP, you can think of it as a basic glue that keeps the internet connected. Uh, so, so given that that is the BGP basics of the BGP protocol, just to look at one extra detail about that, when a prefix P on the left is connected to an autonomous system one, so this could be your local ISP provider uh, to which your company's network is connected, or it could be your own company's AS1 could be your own company's autonomous system, and it consists of border gateway protocol, border gateway routers, which speak to other border gateway routers in neighboring autonomous systems. And so AS1 will announce an update P/AS1 to AS2. And now AS2 from that knows that the network P can be reached through AS1, through its neighbor AS1. And as the update propagates, each AS appends its own AS number to the update. And AS5, for example, when it receives this update, it looks at the AS path. AS path consists of the sequence of ASs, and that sequence of ASs is AS5 knows that that is the sequence of ASs through which the data packet will go. Once it receives that update and installs it in its routers what we call forward information base or FIB. So that enters into the routing table of AS5, and then when AS5 receives data packets from its clients, those data packets want to reach a server that resides in the subnet P. Those data packets will traverse the reverse path relative to BGP. So the data packets will go through AS3, AS2, AS3, AS2, AS4, AS3, AS2, AS1 to reach the server on the left. So that's how BGP operates and facilitates clients or users all over the internet to be able to connect to a particular subnet. So that's the basic functionality of BGP protocol. It has the notion of a prefix that is announced, and it has the notion of an AS path. It also has the notion of an originating AS. In this case, AS1 is the originating AS. It is the first one to announce the prefix. And AS5 has to be, all of these ASs, when they receive it, they have to be having some degree of assurance that this advertisement is correct. So what happens in BGP is that the vulnerabilities are of this nature. So the vulnerabilities of BGP are different types. This picture here illustrates some of those vulnerabilities. So this may be like on the left side, this may be my network, and I announce this prefix 192.0.2.0/24. So that network belongs in in my AS, or it's connected to my AS, and I announce that. What happens is that at the so that announcement propagates through the internet, and as I explained before, the announcement goes through AS to AS one hop at a time, and it propagates throughout the internet using the BGP protocol. But if there is some attacker, malicious or even accidental, so for example, this AS on the right side, it announces the same prefix, either unintentionally or intentionally. In either case, it's an attack, and it is called a false origin announcement or a hijack. The same prefix now propagates in the internet from both sides, from the left here as well as from the right, from two different parts of the internet. The same prefix is being announced in BGP, and it propagates. So one of them is the legitimate announcement, and the other one is an attack. So now what happens is roughly like in the middle, like half of the world, because BGP is a path vector, a distance-based protocol. Therefore, the ASS choose the best path based on the shortest distance, typically, and therefore it will half of the internet will believe in the it will take and install the legitimate update, and the other half of the internet will accept the false announcement. So that's a hijack that kind of successful about for about half of the internet. Now something more serious can happen, and they can announce. In this case, it's not possible to announce anything more than a /24 because /24 is the most routers will not accept anything more specific than /24. But there is this notion of sub-prefix hijack where you announce, for example, let me just show you the next slide and then I will come back. So in the case of the YouTube attack, which happened in 2008, YouTube service was brought down, the denial of service attack essentially. YouTube was inaccessible for about 2.5, 3 hours. And what had happened was that YouTube normally announces a /22, and Pakistan Telecom announced a /24 sub-prefix of YouTube's /22. And that /24, the more specific always wins in the internet. If you have a choice between less specific and more specific, you would route an address towards the more specific. So all the traffic for YouTube was directed to Pakistan Telecom, and YouTube experienced basically outage for that period of time. So going back to my previous slide, so in addition to this like hijack, you can also have somebody maliciously making use of unallocated address space. So and then they announce this unallocated address space, and that is called squatting. So that's similar to hijack, but in this case, no one else is using this address space. They steal an unallocated address space, and they may get away for a period of time unnoticed. But this will be typically caught by the Bougon filters. Bougon filters means you have a list of addresses that are currently not announced in the internet because they are not allocated to anyone. So Bougon filters can filter out such announcements if they are operating in your router. And also there are path modifications that are possible. Somebody can remove some of the ASS from the AS path to make the AS path seem like shorter. And because BGP route selection works based on shortest path, they may be fooled into thinking that this path is shorter when indeed it is not. And by doing that, an attacker can try to misroute the data packets through their network, and they may potentially eavesdrop. So there are all these issues related to BGP security. There is also what we call route leaks. The route leaks happens when a prefix is originated by an ISP, and the ISP announces it to its customer, and so in the internet, in the BGP protocol, there is a agreement, there is a standard policy that when a customer receives a prefix from a ISP, it is not supposed to announce that prefix to another service provider or transit provider. The customer can announce it to its customers below, but it should not send it up towards another transit provider. But if they do that, this is a valley trade. So it goes down and comes back up, so that's a valley. And it's called a violation of valley-free routing. So normally routing should be valley-free, but in this case, if the customer is leaking it, then he is violating the valley-free property of BGP announcements. And this is called a leak. And what happens is that typically the second ISP prefers the customer routes over the peer route. It may receive an announcement for the same prefix from a peer, but typically ISP prefers customer announcement. So this ISP, if it's not implementing any route leak protection, it will accept this false announcement or the route leak and announce it to its peers. And then what happens is that all the traffic for this prefix comes to ISP2 and or AS2, and it is routed to the customer AS3. At which point the customer AS is typically not provisioned to handle that kind of large amount of bandwidth. And so this AS will drop all of those packets on the floor typically, or it may misroute or it may do it like some malicious AS may do it intentionally in order for the traffic to propagate through it, and in which case it can potentially eavesdrop. So routing has routing has all these vulnerabilities. So route leaks is another vulnerability that needs to be addressed. And we have drafts that I'm involved in that address the route leak vulnerability as well. I'm not going to go into that today, but I'll talk about addressing the problem of BGP hijacks and also the path modifications that we talked about earlier. Now, I just mentioned the vulnerabilities, and then every month, almost every month, every week, you have new headlines about attacks on the BGP protocol, on the border gateway protocol routers. And so these are the kinds of like news headlines that we often see. I didn't update it. It just goes back to 2017. But if you look back even in the last month, there would be like multiple attacks. Some of them receive like headlines. Some of them may not receive headlines, but still all of them are pretty serious. Just about in November, a couple of weeks ago, or maybe 2 or 3 weeks ago, there was a serious attack on Google Cloud, as well as Gmail and Google Search. What had happened was that that has to do with route leaks, what I talked about earlier. Google announces its prefix to an operator, a network, an ISP in Nigeria, and then the Nigerian AS leaked the Google. It's not supposed to. It can only announce those routes to its customers, not to transit providers. It leaked them, and then a Russian ISP received, and then they forwarded it to China Telecom. So Google traffic from all over the world was now going through, or large part of the world, was now going through China Telecom to Russian ISP, or not China Telecom, some ISP in China, to an ISP in Russia, to Nigeria, and then trying to go to Google. And that should not be the case. Google has large bandwidth connections or peering with major ISPs, and it should follow those links. But instead, it was going through Nigeria, and and the traffic was getting dropped in the process. So essentially, when the traffic was being misrouted, and so these kinds of attacks happen quite frequently. So IETF has been working on a number of techniques to address the BGP vulnerabilities. I'll go into that in a minute. Let me just mention to you quickly what the DDoS attack concern is at the routers. So this is just one slide, and we'll come back to it later in terms of what the solution is. So what happens when DDoS is performed using IP spoofing, IP address spoofing, and DNS reflection and amplification. So essentially, the attacker compromises many laptops or essentially computers, end user computers, and they install botnet. So these all become sources of botnet. They are compromised, and they are used to generate IP packets with a forged source address. So they are now these IP. So they are sending DNS queries to these DNS servers here. So this is an open reflector as well as it acts as an amplifier. If it's the DNS sec, the amplification is even more. So what's happening here is that the DNS requests go to these open reflectors, and these open reflectors then uh, reply back to the DNS query. And that reply doesn't go to the botnets because the botnets are using a spoofed IP address which belongs to a victim. This IP address belongs to a server which is being victimized. So all these responses from the DNS servers will be directed to this victim here because of the spoofed source address. So essentially, a large volume can be created towards the target, and the target can be brought down, and it experiences a DDoS attack. So this can be highly distributed and very effective in generating hundreds of gigabits, up to hundreds of gigabits, even terabit kind of traffic to bring down a target. And so this also happens. And this has solutions at the router. What is called source address validation can be done in the BGP routers to address this kind of a problem. We'll talk about that a bit later. So now coming back to BGP security vulnerabilities, I've already talked about prefix or sub-prefix hijacking, prefix squatting, AS path modification, where the attacker tries to modify the AS path, making it look like a shorter path and therefore attracting the traffic through itself. Uh, so AS path modifications and then route leaks, I mentioned that. So so these exploitations obviously result in DOS, DDoS, spam, eavesdropping of user data, etc. So the secure IETF created a secure inter-domain routing working group almost 10 years back, and that worked extensively and produced many RFCs that address the BGP routing vulnerability in terms of like two aspects of it: the hijacks, false origin attacks, and also the path modification. So how do you protect how do you detect that the origin is wrong or invalid? How do you detect that the path has been modified? So those two I will talk about today. There are other aspects of BGP security solutions, such as for the route leaks, such as for DDoS mitigation, the source address spoofing. I'll also speak about them briefly, but I'll focus more on the prevention or detection and mitigation of BGP hijacks, and also the technology that is called BGP sec for AS path protection. So we'll go into those two in more detail. So, like I mentioned, the CIDR working group, it is dormant now, but there is another working group called CIDR Ops, Secure Inter-Domain Routing Operations, and that is active, and that is because the standardization for the basic security solutions has been completed. Now we are moving towards operations, right, with the implementation of these techniques. So now the emphasis on operations, and that is why CIDR Ops working group was formed. But these are the kinds of documents that the original CIDR working group produced. They have to do with, first of all, setting up an infrastructure to support secure internet routing. And here we talk about RPKI, resource PKI, which some of you I'm sure have heard about. I'll explain what that is, resource PKI, and then along with that goes route origin authorization. So this is authorizing which prefix can be announced by which autonomous system. This is all cryptographic. You can cryptographically verify the assertions, and based on that, you can do the correct routing. You can reject, potentially you can reject the invalid announcements and only accept the valid announcements. And by doing that, you can prevent hijacking, of course, and also some of the techniques are applied to AS path validation as well. And that is RFC 8205 BGP-SEC protocol specification. I'm a co-editor on that. So this was extensive work extensive work done over several years, a lot of details, backward compatibility with BGP, all those were addressed. So I'll talk about that a little bit. Then I wrote a document on route leaks definition and classification as well. That's an RFC. And there are other RFCs, for example, 7454, which deals with digital operations and security. So this is just a few. There are like a couple of dozen important RFCs related to this. Once you get involved, all those RFCs will be important and interesting to look at. In terms of NIST's latest activity, like NIST publishes what we call special publications. They are all 800 series documents. So I wrote one together with other NIST colleagues. This is almost 10 years old now. We are updating it, and we are in the process of updating this draft. So this draft is ready and being internally reviewed before it is released for the public. And that we expect that will happen within the next few weeks. And it addresses RPKI and origin validation. It describes what those technologies are and makes security recommendations in those areas. It describes BGP-SEC path validation. BGP-SEC path validation is not yet available in routers, but origin validation is available already in commercial routers such as Cisco's and Juniper's and Alcatel, which is now Nokia. So it describes the BGP-SEC path validation, but doesn't go into making any security recommendations regarding that at this point. It will do that when the technology starts to get deployed. All right. And then route filtering is a fairly advanced technology. It describes that and makes security recommendations, as well as regarding source address validation for mitigation of DDoS. So this is something that will be forthcoming fairly soon. And I'm an author on that, the leading author. So now let's focus on like what this RPKI is and what BGP origin validation is. For that, essentially what you have in the internet is the resources that your company gets in terms of IP address space, the prefixes that it can use to deploy its servers as well as to create your internal network. And you announce those prefixes in the internet. You have autonomous. Your organization may have an autonomous system as well and an autonomous system number. So these are resources, and these resources are allocated from IANA down to the regional RIRs. RIR being routing registries, internet registries. And the RIRs in turn allocate sub-allocate the address to ISPs such as Tata Telecom or Reliance, etc. So there's a hierarchy of allocation of these resources. Then there is the notion of route origin authorization. which binds the announcement of a prefix to an autonomous system number, and then there is a notion of signing the updates that has to do with path validation. I'll describe that later. And once these things are in place, what happens is that the receiving routers throughout the internet can validate the origination of a prefix announcement by using the route origin authorization. So I'll go into some of the details related to this technology and the standards. So there is the XDOT 509, which is cryptographic assertion of allocations and sub-allocations of resources. Uh, and so essentially the resources that are allocated by the route, by the trust anchor, the route to its child. So it starts from there, and then there is a hierarchy of sub-allocations. So the basic dot 509 is used with some extensions to create the resource PKI infrastructure. So basically, resource certificates are allocated. These are signed digital certificates that certify that you are given these resources, and that has established the authorized use for you of those resources. And so essentially, it starts with IANA, the allocation, and then the allocations go to their various regional internet registries or RIRs, and those are in Africa, Asia Pacific, which includes India, ARIN, Latin America. ARIN is for North America, Latin America, and Europe. And for example, if you take the ARIN case, it will allocate resource search to various enterprises and major ISPs such as AT&T or Verizon or Sprint, and they will in turn announce, sub-allocate and issue resource certificates. So the Chinese, right now the trust anchors for the resource certificate issuance, they don't start, unfortunately, from one point like IANA. IANA is still allocates, it's at the top in terms of allocation, but in terms of the signing of the resource certificates, the trust anchor is one level below, and there are 5 trust anchors currently. Ideally, we should have only one. And ARIN allocates and then issues resource certificates to the enterprises ISPs, and then ISPs may further allocate resource certificates to their customer ISPs, and then there may be small companies, small enterprises that get their resource certificates as well. So this is the chain of allocation as well as resource certification. Now, once you have so it comes down, your enterprise gets a resource certificate. This customer is essentially a customer of a transit provider, such as Tata Telecom, say, and then this could be a company in Delhi or Bangalore or Hyderabad, a small company, medium-sized company, what have you. So they have some prefix that is allocated to them. Their servers are placed with addresses in that prefix, and they want to protect their prefix. Somebody else from other side of the internet should not be able to hijack it. So they create what is called a ROA. ROA is a signed object, route origin authorization, and it associates the prefix with a valid origin ASN. So they may have their own ASN, and they may assert that in the ROA that I announced this prefix from my this AS number, which could be their own AS number, or it could be their transit provider's AS number, either way. So once this ROA is signed, then it is placed in an RTKI repository, and ARIN, RIPE, all these RIRs maintain repositories, and there may be other repositories as well that may be third-party services. But in any case, the ROAs reside in registries or repositories that we call RTKI repositories. and then what happens is once you have created a ROA for your prefix, for your enterprise prefix, um, these ROAs are downloaded by what we call caches, RPKI caches. Let me go through them. So essentially there are the repositories which may be maintained by RIRs or big ISPs, may maintain repository as well. Those are downloaded to RPKI validating servers that are in your network or in your ISP's network, transit provider's network. And then from there, there is this RPKI router protocol, which is RFC 60 to 10 as well as 80 to 10. So RPKI router protocol is used to propagate RPKI. I mean, this is this is like what you call whitelists. In the cache you can generate in your network in the RPKI cache. You are taking all this RPKI data. You are looking at the ROAs, and from the ROAs you can generate a whitelist of the prefix and the origin AS that are valid, and those are fed to the routers. And in the router now, any BGP announcement that is received, they can check them against this white list of prefix origin pairs. And by doing that, they would be in a position to mark an update as valid or invalid or not found. I'll explain what not found is. But essentially, it's in a position, if everybody adopts this technology, all the routers in the internet can characterize each update as either valid or invalid, and invalid would be clearly a hijack. It's not expected, that origin is not expected, it's a hijack, and those will be rejected. By doing that, we can totally prevent hijacks. So the question is like the adoption. So right now, I'll show you what the adoption level is right now. But before that, I just mentioned to you that each update is marked, it is validated using the ROA data, and by using this kind of an algorithm. And the result of the algorithm would be valid if the prefix and the origin AS match. And there is also something else called max length, because you may be allocated, like your ISP, for example, may be allocated a large address space, such as a /15 or something, and they create a ROA for their /15, and they also sub-allocate to their customers, and then they can create ROAs for their customers also. So they manage that whole thing. Your ISP can potentially manage it for you, as well as for themselves, creating the ROAs and making sure that all the ROAs are in place that come from this ISP, all the BGP updates that come from this transit provider, and they can also take care of their customers. So in any case, the ROA data says that this prefix can be originated legitimately from this AS, and also it specifies what's called a max length. Max length means that the prefix owner says that I have a /22, and I will announce up to, I have let's say a /16, and I will announce up to /24. I have some prefixes that go up to a /24, and it can specify all those prefixes in the ROA and say that of my address space, I will announce the /16, and I will announce some /18, some /20, some /24s, but nothing else. So it doesn't create ROAs for anything else that it doesn't intend to announce. In which case, the routers that download the ROA data look at that, they compare the AS number, they compare the prefix length, and they determine whether it is valid or invalid. So AS number should match, the prefix length should be less than the max length.
This is not more load for the router actually in terms of doing all the work.
Yeah, we have measured that.
And create an impact of the traffic routing.
Yeah. So the question is, will it not generate more workload on the routers, and will it not, for example, slow down the convergence of the routing table? So that we have measured it, and other organizations have also measured it. So some of the work is happening offline, and some of the work is happening in line or in real time in the routers. So the work that is happening offline is in the RPKI caches, and then it's in the routers that the whitelist is fed, and then the matching, the validation is happening in real time. And in terms of the workload, to answer the question, the measurements show that that is minuscule. It's in the range of 2 to 7% in the worst case. So fairly small impact on the router's processor.
So the benefits outweigh
The cost. Yes, right. Uh, so the third state here, you may be curious what that is not found. It's in partial deployment situation. Not all the prefixes have ROAs. Some people have created ROAs, some haven't. And so if a prefix does not have a ROA and that is announced either by the legitimate owner or a malicious actor, in both cases, what happens is that this announcement is received with some AS, and there is no ROA created, so it is not known what is valid AS for this prefix, and therefore the outcome in this algorithm is not found, meaning that we don't know because there is no ROA. So that's the majority of the cases right now, and so then you need some algorithm to decide when you. So this outcome, valid, invalid, not found, is input into the path selection process. And in the path selection process, normally you apply, I prefer customer route over a provider or peer route. That is one policy that you may apply. And typically ISPs apply that policy. Then another policy would be if it is valid, then I would definitely consider it in path selection. And if it is invalid, I would definitely throw it away, not accept it. And then if it is not found, then if I don't have any other choice, I only have a not found, I'll accept it because so far nobody has created a ROA for it. So I don't know whether it is valid or invalid. So that's the idea, how it will play in path selection process in the policy in the router. In terms of the implementation status, the adoption status, all the five RIRs have implemented RPKI and they maintain RPKI repositories. Major vendors, Cisco, Juniper, Nokia have implemented origin validation. You can turn it on today if you have these routers. And then you're in a position to detect what looks like potentially hijacks, and you can reject them, drop them if you like. Uh, they use for the signature? They have to have some digital certificate, right? And then they use the private key corresponding to that. And where do they get the digital certificate from? So you go back to the RPKI, which we showed earlier. So there's this hierarchical allocation, sub-allocation, and the RPKI, we already talked about RPKI. The same thing is used not only for prefix certification, but also for autonomous system number certification. Autonomous system number is another resource. And so ASNs also receive, we also receive digital certificates for the ASN for your autonomous system. So out of that, you generate router certificates and you install them in the routers in your autonomous system. So the BGP routers now are equipped with a private key to sign the announcements that they send to their neighbors. And the neighbors can download the public key corresponding to that. The key identifier, the subject key identifier is provided in the update. AS2 will look at the SKI1 and it will fetch the public certificate, the certificate, and from that it will get the public key corresponding to AS1, and then it can verify the signature. So signature 1, 2 can be verified by AS2 or AS3, any of these ASs, by looking up the the resource certificates and derive and getting the public key from there. And they use the public key to validate the update or verify the signatures. And by doing that, they validate the updates. So that's the process of validating the update. So as I said, it involves cryptographic processing on the routers now, which we don't have currently. And we will not have that with origin validation. We have maybe tier 3, and then finally stop there. That's one the practice and so on. You can save them from having to invest too much to upgrade their routers by reducing the amount of processing that they need to do. And we do that by the simplex scheme, where all that we propose is that if you are a stub AS, then you don't need to receive signed updates. You request your service provider to send unsigned updates like you get today. You do origin validation if you wish, or you can trust your transit provider. But typically, you should do origin validation yourself. But you don't do path signature validation. You don't receive path signatures and you don't do path signature validation. the ISP does it for you, and you trust the ISP regarding that. By doing that, so it's called simplex BGP-sec. So the stub router will sign the updates towards the transit provider or multi-home transit providers, but it will only receive unsigned updates. And that substantially decreases the amount of processing in the stub ASs. So with that, with simple software updates, without any hardware update, they can adopt BGP-sec. And the transit providers are more resourceful. So anyway, every 5 years, they upgrade the BGP processor. And when they upgrade it, typically, historically, every 5 years, the processing speed doubles or more than doubles. So if that happens, they can keep up. If you can keep doubling it, we have done analysis on the processing burden on these routers due to BGP-sec path validation. And if you so a certain amount of additional capacity in the processing is required, and if BGP-sec BGP routers are upgraded to roughly double their processing capacity for BGP every 5 years, let's say, then it's possible to show that these ISPs, the transit provider ISPs routers can keep up with the additional processing that is required. So you have this trade-off. You have to have faster processors, which does happen anyway every 5 years or so, but you have the benefit of path validation. All these path attacks can be detected and prevented. So 84% are stubs and 16% are non-stubs. So with the simplex, it benefits these 84% of the routers. So they have very little upgrade expense. But the 16% non-stubs are anyway transit providers and such, and they anyway upgrade the routers more frequently, say every 5 years. So it is possible for them to do that and be able to adopt BGP-sec. So we'll see how that goes. We have done some detailed like computations and done some optimizations to show that you can speed up both signature signing processing as well as verification processing. So we have seen like more than doubling. We have optimization algorithms that we have worked on this with a contractor outside of NIST, and together we have come up with some optimization techniques that allow you to do the processing of like the signature verification on the BGP updates more than twice the speed of what the fastest processing that you can do today with OpenSSL, for example. So there is promise to be able to speed it up significantly and reduce the processing delay, the workload, and speed up the convergence of the routing tables. And like I said before, I jumped a little bit ahead. Like I said before, if you are able to, so this is a little complicated. It shows the relative convergence time. So assume one is the convergence time like today, or this was in 2015. And then you say, okay, at some year into the future, what will be my convergence time with the BGP-sec? If BGP-sec path validation is adopted and all these signature dates, and they have to be verified. And we are also assuming some adoption curve, the normal adoption curve, and we are also assuming routing, the route processor doubling up in speed every 5 years, which has been the trend in the past. So hopefully that's not a new assumption. So every 5 years, if you double the speed, the convergence time drops because the processor has been doubled in speed. And then the traffic is going up because IPv4, IPv6 prefixes they are increasing in number because there are more prefixes are allocated, more prefixes are announced. So the BGP traffic increases. And then again, after 5 years, if you introduce a faster processor, again, the convergence time drops So we are comparing here what BGP, like not doing any BGP sec, only BGP with the origin validation, or BGP sec with the path validation. And so they are if you don't do path validation, your performance is even better. But even if you do path validation compared to like what you have today, there can be a slight trend downwards if you are able to speed up every the double the speed every 5 years roughly. So not, I mean, and this is happening because of optimization algorithms. Uh, Potentially, this can happen because of multiple reasons. Uh, Doubling of the router speed, for example, every years. Optimizations, software optimizations for the cryptographic processing. Then parallel processing, multiprocessor implementation of the BGP-sec processing. So all of these combined can give you this kind of a speed up, and hopefully it can keep the convergence time from getting worse. So there is some hope or possibility there. Can I spend another 5 minutes? So at this point, like on everything that I've talked about, before I go into this DDoS mitigation and source address validation, it will only take 5 minutes. Any questions that you want to ask regarding origin validation, path validation?
Yeah. So in the previous slides, there was a like from AS1 is AS2 the hop. So
Yeah.
the data is traveling from one hop to another hop. So while the data is traveling, each and every hop is signing on their data.
Yeah.
So for signing that data, the digital certificate is being issued by IANA or some other organization.
Right. So IANA actually, unfortunately, is not a trust anchor. They are not playing the role of trust anchor. It would be nice if we had a common trust anchor, not necessarily IANA, any organization. Right now, the trust anchors are the 5 RIRs, and they are issuing digital certificates for both the prefixes and also the autonomous systems. So you're right. The not IANA, but that tree still applies. The RIR, for example, for India, APNIC will sub-allocate some prefixes to say Tata Telecom and Reliance or Airtel, and they will in turn allocate them to triple IT or various companies, enterprises, etc. Uh, so certificate authority that comes from your ISP. If you are an enterprise, it comes from your ISP. And now this you can use this CS certificate another solution, but let's talk which is done in PGP. So how that works is AS2 will say, I will only allow packets to be received from you with source address that belongs in whatever prefix you announce to me. You announce P1 to me. So any data packets that comes from you to me, I will accept the data packet only if it belongs in an announced prefix. First path filtering insists that if you announced it and I installed a route towards you for this prefix, then I'll announce data packet with address. Otherwise, I won't accept your data packet. In this case, now it gets tricky because you have multi-homing kind of a situation. And this is called RFC 38 and RFC 84, which address this, which describe this solution. Now, it's tricky because it's not good that what we are seeing here, if this URPF is not good, it's not working the way we want it to work. Because this AS1 is free to send data packets with source address either in P1 or P, because those two prefixes both belong to it announces them, and those are connected to it. And I give you the I'm going to and it doesn't say. This are at the level of the BGP routers in the autonomous systems. But at the level of the IoT devices, there is one effort in the IETF called MUD, manufacturing usage description. So what MUD does is that for each IoT device that are, if you follow the MUD technique for protection from DDoS, from you can potentially suppress many of these DDoS attacks. Um, does that address your question?
Yeah.
So the low power doesn't matter because it's not doing this kind of cryptographic processing. The low processing, the low memory doesn't matter because that is being done at the edge device, which is looking at the traffic and denying the traffic unless it follows the MUD profile. So it restricts the IoT device to following the MUD profile. Anything else it considers it as an attack. So IoT device doesn't itself do anything really, except to download the profile and try to behave according to that profile and not violate to outside of the profile. You were saying something?
Yeah, I mean, the DOS attacks are more, more prominent on the low processing process. The low, what I was trying.
Yeah. So there are, the NIST is working on other documents. I talk about DDoS mitigation in the routers, but there is another document that NIST is working on separate one, where the vulnerabilities of IoT are addressed. I can provide the point.
Is there a chance to make the local networks 100% secure?
By local networks, you mean enterprise?
Local networks where you don't have the internet connectivity, just the local
Or
connectivity. Ad hoc
intranet.
Yeah.
No, I'm sure your answer is no.
Yes.
Yes, go ahead.
Actually, there's no security for local purpose. We need to apply certificates to provide the security for the local adapters. Okay. Otherwise, firewalls or third-party tools like that, you can apply it. Unless there is no security.
So your network, this local network is not connected.
It's not connected.
So then what is the vulnerability there?
So there might be an attacker within the system itself.
Within this. So then you would use authentication technique to authenticate, maybe two-layer authentication, what have you, to authenticate each user when they connect to the network. And then there can also be role-based authentication. If somebody is a manager, they can do certain things. And somebody is like from this IT division, meaning the CIO, they have more permissions to to more in terms of like where they can go in the network. But the common end user, like the engineers or the secretaries, will be limited in terms of it. So all of those can be implemented. NIST has recommendations. So um, there are enterprise security recommendations. Whether they are connected to the internet or not, you can follow this.
I also have one more question from a remote participant. Just a second. So the question is locally, how to secure a web server without using CA certificates and local certificates? Do HTTP encoding help in IoT local networks between the IoT hub and the app? Sure. So the question says, locally, how do you secure a web server without using CA certificates and local certificates? Also, do HTTP encoding help in IoT local networks in between the IoT hub device and the mobile app?
So yeah, so that's not my area of expertise. I hear the words, I think I understand the question. It has to do with, like again, managing an enterprise network, which includes IoT devices. So potentially the MUD profile, the MUD technology, the MUD specification from IETF can be used. But then there are other enterprise best practices, authentication, etc., that can be potentially applied. So I'm not sure about the complete answer to that, but I think those are some potential pointers. That's why the only one in the remote person. How many did you have? And it worked? Or
so, since the networks are huge, and the peer nodes which comes adds to the network, and some goes out of the network sometimes. So all those events are being time dependent, and um, nowhere time even considered when you consider overall. So, is there any nodes which takes care of synchronizing time? So, how the time synchronization is come to the picture?
so, yeah, you may be asking. So the question is about a different prefix announcement come at different times. One thing, and there are also changes that prefix is announced and then it is withdrawn. So there are these dynamic changes in BGP announcements, and as well as I think we are talking about the time synchronization. Do different routers in different autonomous systems, are they totally like well synchronized with respect to time? That's also part of the question. So there is a lot of time dynamics, obviously, in BGP because there are announcements and withdrawals and then re-announcements. And then, the question just didn't go there, but I would also add that there can be changes in RPKI. You create a ROA, and for some reason, that ROA gets dropped at the repository, or your the connection from your RPKI cache in your autonomous system to the repository temporarily breaks, and you are not able to download all the ROAs from everywhere. So all these dynamics are important. They create churn. They create potentially not inaccuracy, but more if like if you had updates valid or invalid now and not found, now you are not able to judge validity of some origin, BGP origins, because of the dynamics of the RPKI and the connection. Sometimes like you lose a connection to an RPKI repository. So those dynamics happen. So the basic BGP dynamics is not an issue. That is fine. That is well covered. The RPKI or origin validation has no problem. with the basic PGP temporal dynamics. That's perfectly normal. But what you are asking, if one of your questions is going like getting at like the robustness of the RTI repositories, RTI data. So for that, you can use some TCP, for example, TCP security mechanisms. So things like that. And in terms of time synchronization, I think the routers are very well positioned. Regard to that, there is an NTP network time protocol. They are well synchronized today. Like that's how they operate. They interconnect and don't have issues with regard to the timing within each router. That is reasonable.
I would like to add a little bit for the time synchronization part. So we have this 6-stage group which just works for the time synchronization, particularly for the IP networks. There's not much look.
How inside whether information is being sent from one year to another year is faster than
Oh, okay.
other activity.
Right. So this is there are delays in receiving BGP updates from different peers. So you may have receive an update from your customer for a prefix, and you may receive an update for the same prefix from a peer or from a transit provider. So you always get multiple announcements, and they don't come at the same time because there are different transmission delays, different path lengths in terms of the distance, etc. Right, the speed of light kind of delays. So they do come at different times, and the router makes a decision once, and then few milliseconds later, another update comes. Then it again includes that in the decision process. Now it has the previous update and the update that it just received, and it reruns. I mean, every time it gets the update, it reruns the decision process. It's not like you do it once and then you stop for a day or a week. It doesn't. BGP doesn't do that. BGP reacts to each update as and when it comes. So if there are multiple updates, they are still shifted in time with respect to each other for the same prefix. That doesn't matter because I may make one decision in my router now, but a minute later or even 30 milliseconds later, if I get another update for the same prefix, I again do the best path once again. So by doing that, I always have the best path based on the updates that I have currently received. So yes, what you are talking about is it is called path hunting, meaning that you settle for one best path now, and then a few seconds later, your best path changes because some other update arrived slightly delayed in a different path. That may not be your best path, then there is no churn. Then the BGP churn doesn't happen. But if you select that as the best path, then what we call BGP path hunting happens. And you are switching from one path to another path to another path. And eventually it will settle down. But it does produce some churn.
I was to go upstream generators necessarily takes 1 year, 2 year, also upgrade. There's not a lot of cannot adopt this category. So typically the lag behind the implementation in such cases, it's not API talked about. This package is more valid, not valid,
Not found.
not valid. You want to
Oh, if Microsoft or a particular enterprise X has not adopted RPKI and route origin authorization and origin validation, what happens is that their prefixes that they announce will be not found everywhere throughout the internet. Any router that does origin validation will determine this enterprise access prefix to be not found, meaning that I cannot say whether it's valid or not valid because they don't have it. So that is partial deployment, and in that case, if nobody is hijacking Simon at the same time, this enterprise X is announcing and nobody else is hijacking, then there is no issue because the router says I have not found and I don't have an alternative route, so I will select this route even though it's not found. So that's fine. But suppose there is a competition, there is this not found and somebody hijacked, and both are not found. Then the router will end up selecting the shortest path, and hijack may succeed, but that is why the adoption we have. It's important for the adoption curve to keep going up, and when it reaches a critical limit like 95% or more, then we are good. For the large part of the internet, we are good, and a lot of hijacks are both accidental and malicious can be prevented.
national security for internet communication tools. Is there any proposal which talks about in terms of frequency as in combination with both? So if I need a frequency of communication, maybe some data would be meaning some isn't contributes to the
Do you have like the BGP updates in mind, or do you have the data packets in mind? So yeah, if you're talking about BGP updates, we talked about that. I think, yeah.
in addition to the point which you said the system can define explicitly the value addresses. So and one defines the IP value addresses and then the other IP addresses cannot be spoofed kind of stuff.
So yeah, I think your question is a little complex. Basically, things we talked about today are trying to protect the BGP updates, and so that part of it is fairly distributed. It can independently do its own validation, and that would work pretty well. There's little concern about that. Origin validation will work to prevent all accidental hacking. If you are concerned about data packets and between two adjacent routers, if the data goes in a TCP session or what have you, then there is encryption. If you are concerned about data protection, there is encryption at the application layer that protects data packets. Is that where you are going, like, or other questions? We can talk, and maybe we can wrap up the session and then you and I will talk after the.
So thank you everyone for your patience throughout.
Thank you, Dr. Sriram, for your valuable insights on the threats to network security, border gateway protocol, and things which we had never heard of. So now I would like to invite Dr. Hari for extending a momentum of love to Dr. Sriram, followed by a vote of thanks by Adarsh.
Once again, I would like to thanks Sriram, sir, Dr. Sriram, sir, from Mr. Alur, for coming there and giving a nice talk about the concept. And also, I would like to thanks Ranjit from the Switch organization and the Triple IT, and also from ISOC, the Subhashis, and the ISOC Hyderabad chapter for making this event successful within a short period of time. And also, we have the attendees from here as well as from remote. We are like 10 plus of an all over the world, global attendees, even from Asia, Europe, US, UK. We have multiple attendees. So this session is recorded. It will be available online from the ISOG, and also presentations will also be available. I would like to thank each and everyone, and also for the sir for specially thanks. Thank you. I enjoyed the
Likewise.
I'd like everyone to join for a group photo. Please.